In my today's lecture, I want to discuss the geothermal energy sources. The content of the today's lecture is the introduction to geothermal energy, geothermal structure of the earth, geothermal region in the earth, and the types of geothermal resources. The geothermal energy sources. Now come to the introduction part. The word geothermal comes from the Greek words geo. Geo means earth, and the thermi. Thermi means heat. Geothermal energy is heat from within the earth. A geothermal resource can be simply defined as a reservoir inside the earth from which heat can be extracted economically, cost-wise less expensive than or comparable with other conventional sources of the energy such as hydroelectric power or the fossil fuels power, and utilized for generating the electric power or any other suitable industrial, agricultural or the domestic application in the near future. A geothermal reservoir can contain heat both in the solid rocks as well as in the fluids that fill the fractures and pores spaces within the rock. It is a clean, renewable resource that provides energy around the world. It is considered a renewable energy resource because the heat emanating from the interior of the earth is essentially limitless. The heat continuously flowing from the earth's interior is estimated to be equivalent to 42 million megawatts of power. 1 megawatt is equivalent to 1 million watts and can meet the power needs of about 1000 homes. The interior of the earth is expected to remain extremely hot for billions of years to come, ensuring an essentially limitless flow of heat. Geothermal power plants capture this heat and convert it to energy in the form of electricity. Estimates of geothermal resources are made on the basis of geological and geophysical data such as depth, thickness, and extent of the geothermal aquifers, properties of rock formations, salinity and geochemistry of fluids likely to be present in the aquifers, and the temperature, porosity, and the permeability of the rock formations. A geothermal resource is distinct from a geothermal reserve, which refers to the part of a resource that can be extracted economically at the present price level. Now come to the geothermal structure of the earth. This is the geothermal structure of the earth. There is the 4 layers in the geothermal structure of the earth. The inner part is the core, then the outer core, then the mantle, and at last the most outer surface is called the crust. The crust is about 30 kilometer, and then up to the 2900 kilometer is mantle, then the 5180 kilometer is called the outer core, and from 5180 kilometer to 6370 kilometer is called the total inner core. To the depth above the 6,370 kilometers is called the inner core. The geothermal energy is generated in the Earth's core, almost 4,000 miles beneath the Earth's surface. The double layer core is made up of very hot magma, melted rock surrounding a solid iron center. Very high temperatures are continuously produced inside the Earth by the slow decay of the radioactive particles. This process is natural in all rocks. Then the surrounding the outer core is the mantle, which is about 1,800 miles thick and made of magma and rocks. This is the mantle. From 30 kilometer depth to the 2,900 kilometer depth, this layer is called the mantle. It produced more than 1,000 degrees centigrade heat. The outermost layer of the earth, the land that forms the continents and the ocean floors, is called the crust. This is the crust. The crust is the 3 to 5 miles thick under the oceans and 15 to 35 miles thick on the continents. The crust is not a solid piece like the shell of an egg, but it is broken into the pieces that are called the plates. These blue lines are separated. The blue lines separate the different types of plates. The magma comes close to the Earth's surface near the edges of these plates. The Earth's crust is broken into huge plates that move apart or push together at about the same rate at which our fingernails grow. Convection of semi-molten rock in the upper mantle helps drive the plate tectonics. The most active geothermal resources are usually found along the major plate boundaries as shown in the figure. These are the boundaries. The blue lines indicate the boundaries of the plates, where the earthquakes and the volcanoes are concentrated. Most of the geothermal activity in the world occurs in an area known as the Ring of Fire. The Ring of Fire rims the Pacific Ocean and is bounded by the Japan, Philippines, and the Aleutian Island, North America, Central America, and the South America. This is where the volcanoes occur. The lava that erupts from the volcanoes is partly the magma. Deep underground, the rocks and the water absorb the heat from this magma. The liquid magma has a lower density than the solid rock around it, so it tends to move upwards towards the Earth's surface. The majority of the time the magma stays underneath the Earth's surface and heats up the rock and pockets of the water that it comes in contact with. Sometimes the magma actually finds its way through the Earth's crust and vents through the volcanoes as lava. Most often, the humans have not used the geothermal energy from the magma directly. The humans have spent much time exploiting the water tables that are heated by the magma. These water resources are very often vented to the surface by the cracks in the crust called the fissures. Once the heated water has reached the surface, humans can then put it into a variety of uses. We can dig the wells and pump the heated and underground water to the surface. People around the world use the geothermal energy to heat their homes and to produce the electricity. The picture shows the source of the geothermal electric power production heat from the earth. As depth into the earth crust increases, then the temperature increases as well, as shown in the figure. There are three classes of geothermal regions. One is called the hyperthermal, second is called the semithermal, and third is one is the normal. The hyperthermal, where the temperature gradient is greater than 80 degrees centigrade per kilometer. These regions are usually on tectonic plate boundaries. The first such region to be tapped for electricity generation was in 1904 at the Ladirello in Tuscany, Italy. Nearly all geothermal power stations are in such areas. Second is called the semithermal, where the temperature gradient is approximately 40 degrees centigrade per kilometer to 80 degrees centigrade per kilometer. Such regions are associated generally with the anomalies away from the plate boundaries. The heat extraction is from harnessing the natural aquifers or the fracturing dry rocks. A well-known example is the geothermal district heating system for houses in Paris. Third one is the normal. The temperature gradient is less than 40 degrees centigrade per kilometer. These remaining regions are associated with the average geothermal conductive heat flow at around 0.06 watt per meter square. It is unlikely that these areas can ever supply the geothermal heat at the prices competitive to the present or the future energy supplies. In each class, it is in principle possible for heat to be obtained by the following, that is natural hydrothermal circulation, in which the water percolates to deep aquifers to be heated to dry stream, vapor liquid mixtures or the hot waters. The emissions of each type may be observed in nature. As shown in the figure, this is the natural hydrothermal circulation of the hot water, vapor or the liquid mixtures that are emitted from the ground to the surface. If the pressure increases by the steam formation at the deep levels, the spectacular geysers may occur, as at the geysers near Sacramento in California and in the Wairaki area near the Rotorua in New Zealand. Note that the liquid water is ejected and not the steam. Second is the hot igneous systems, which is associated with the heat from the semi-molten magma that solidifies to the lava. The first power plant using this source was the 3 megawatt station in Hawaii, completed in 1982. Third one is the dry rock fracturing. Poorly conducting dry rocks, mainly granite, stores heat over the millions of years with a subsequent increase in temperature. Artificial fracturing from the boreholes enables water to be pumped through the rock so that the heat can be extracted. Now come to the types of the geothermal energy resources. The essential requirements for a geothermal system to exist are a large source of heat, a reservoir to accumulate the heat, and a barrier to hold the accumulated heat. There is a suit for geological conditions that could result in a variety of geothermal systems. Consequently, all geothermal fields differ from one another. However, depending upon certain common characteristics, these are broadly classified into the following categories. Number 1 is vapor dominated, number 2 is the hot water, and number 3 is the geopressure, number 4 is the hot dry rock, and lastly it is magma. So come to the first type of categories, that is called the vapor dominated geothermal fields. Most of the presently exploited geothermal fields contain the water at high pressures and temperatures in excess of 100 degrees centigrade. When this water is brought to the earth's surface, the pressure is considerably reduced, generating large quantities of steam, and a mixture of saturated steam and water is produced. The ratio of steam to water varies from one site to another. Some of the best known geothermal fields, such as the Rio Preto, Mexico, Waireki, New Zealand, Reykjavik, Iceland, Salton Sea, USA, and the Otek in Japan, belongs to this category. Since the steam associated with the water is produced in this field, they are known as the wet steam fields. There are a few other important geothermal fields, such as the Ladirillo, Italy, and the Geysers, USA, which produces the superheated steam with no associated fluids. The figure shows the model representation of the vapor-dominated field. The fields of the latter type are known as the dry steam field. The basic requirements of the vapor-dominated geothermal fields, whether of the dry steam or the wet steam type, it is include the adequate supplies of water in addition to the three prerequisites. One is the large source of heat, another is the reservoir to accumulate the heat. This is the reservoir to accumulate the heat. This is the heat source. And third one is the barrier to hold the accumulated heat. So this is the barrier. Now come to the heat source. The fact that the vapor dominated geothermal fields are suited in regions of the recent volcanism, some of them being located on or close to the volcanoes, has verified that magma is there as a source. Young, high temperature 500 to 1000 degrees centigrade magma intrusions to within the depth of a few of several kilometers from the Earth's surface allow the necessary heat to be accumulated in the economical quantities. In hard compact rocks, faulting may provide a channel for the magma to reach the surface. Soft or plastic rocks, when present, can flow and block the fault space, causing the magma to spread at the contact between the soft and the hard rocks. Active volcanoes, fumaroles, hot spring, and the geysers are the obvious surface manifestations of the recent volcanic activities. In addition, the certain geological environments such as regions of quaternary uplift and the regions of late tertiary and quaternary subsidence are indicative of the shallow magnetic intrusions. Now come to the second element, that is called the reservoir and the water supply. This is the reservoir, hot fluids, and the cold meteoric water. In order to form a heat reservoir, the anomalous magnetic intrusion should encounter the porous and permeable water-filled rock strata. Within the reservoir, the convection currents of the hot water and or steam are set up, providing a good heat exchange, and the temperature difference between the top and the bottom of the reservoir is not very significant. A variety of rocks have been found to constitute the good reservoirs. Good reservoirs could also be formed at the geological unconformities and the formation boundaries, provided that they are permeable and have the good hydraulic continuity and the water supply. Now come to the cap rock, the third element of the vapor dominated geothermal fields. The cap rock is the geochemical processes associated with the geothermal fields, such that the hydrothermal alteration of rocks and mineral deposition are helpful in sealing of the fissures. Typical examples of cap rocks rendered impermeable through chemical reaction and deposition are seen at the geysers and the Wotek geothermal fields. At the geysers, the calcite and the silica field fractures up to the 1 in wide are commonly seen. Evidence of the hydrothermal alteration is presented by the bleaching of grey wax as well as by the absence of vegetation in patches. The geochemical and the hydrothermal processes are complicated and vary from the place to place. Now come to the second type of geothermal energy sources, that is the hot water geothermal systems. In hot water geothermal fields, the water convection currents carry the heat from the deep source to the shallow reservoir. The bottom of the convective shell may be heated through the conduction from the hot rocks. The geology of the hot water geothermal fields is quite similar to that of the ordinary groundwater system. They differ from the earlier discussed vapor dominated geothermal fields in the fact that the hot water geothermal fields are characterized by the liquid water being the continuous pressure controlling fluid phase. Typically, the temperature of the hot water reservoirs varies from 60 to 100 degrees centigrade, and they occur at the depth ranging from 1500 to 3000 meters. A schematic representation of a hot water field and the reference curve, this is called the reference curve, represents the variation of the boiling point of the pure water with the depth. As shown in the figure, a hot water geothermal field could develop in the absence of a cap rock if the thermal gradients and the depth of the aquifer are adequate to maintain a convective circulation. When the cap rock is absent, The temperatures in the upper part of the reservoir cannot exceed the boiling point at the atmospheric pressure, since with the convective rise the water loses the pressure and also becomes the mixed with the cool groundwater. In the figure, this is shown in the convective circulation of the water. Depending upon the temperature, the chemistry and the structure of the reservoir, the hot water systems have been classified into the several subtypes. The following is a brief description of the types. Number 1 is the systems characterized by low to moderate temperatures, say 50 to 150 degrees centigrade, and producing the water with a chemical composition similar to the regional surface and the shallow groundwaters. Second subtypes is the systems characterized by the presence of partly non-meteoric water. Such systems usually occur in the deep sedimentary basins. Third one is the systems characterized by the presence of brine of very high salinity. The chemistry can vary considerably from the one field to another. The Salton Sea, California, and the Red Sea, the brine pools belong to this subtype and have very differing bulk chemistry of the sediments and the associated rocks, probably attributable to the difference in brine composition. Systems characterized by the presence of natural cap rocks, geothermal fields at the Cerro Prieto, that is in Mexico, and the Salton Sea in California have the cap rocks constituted by the fine-grained, low permeability sediments. Fifth one is the systems which is characterized by the creation of their own self-sealing cap rocks. As explained earlier in discussing the vapor-dominated geothermal systems, these cap rocks are formed through the chemical alterations and depositions of the sediments near the surface, where the temperature decreases suddenly. The Wairiki in New Zealand and the Yellowstone Park in Wyoming are typical examples of this type of systems. Now the third one energy resource is the geopressure geothermal resource as shown in the figure. A type of hydrothermal environment whose hot water is almost completely sealed from the exchange with the surrounding rocks is called the geopressure system. This is the low density high pressure cell, and this is the tertiary SO and SH. This is the coastal plain, this is the continental plain, and this is the slope. Such systems typically form in a basin in which very rapid filling with the sediments takes place, resulting in higher than normal pressure of the hydrothermal water. Geopressure geothermal systems were first identified in the deep sedimentary layers underneath the Gulf of Mexico at a depth between 6 and 8 km with the pore pressures of up to 130 megapascal, and the temperature in the range is 150 to 180 degrees centigrade. The geopressure resources are found when there is an impermeable layer of sedimentary cap rock that traps a geothermal reservoir. The geopressure geothermal resources, in these instances, the weight of the sediment layer and the lack of the permeability increases the pressure inside the reservoir. Geopressure resources typically range from the 90 degree centigrade to 200 plus degree centigrade, and the increase in pressure reduces the energy required to pump the resource, making the geopressure resource desirable. In the United States, the geopressure resources can be found along the Pacific coast, in the Appalachia, and beneath the Gulf of Mexico, and in other deep sedimentary basins. Geopressure geothermal systems pressure much greater than the hydrostatic. Thermal waters under high pressure in sand aquifers are the target for drilling, mainly as they contain dissolved methane. The source of energy available from this type of resource consists of heat, mechanical energy, and the methane gas. Radiogenic resources are found where the granitic intrusions are near the surface, heating up the local groundwater from the decay of the radioactive thorium, potassium, and the uranium. This localized heating increases the normal geothermal gradient, providing the hot water at the economical drilling depth. This type of resource occurs along the eastern United States but has not been developed commercially. Third one is the hot dry rock or HDR geothermal resources. The hot dry rock is an abundant source of geothermal energy available for the use. A vast store of thermal energy is contained within the hot but essentially dry, impervious crystalline basement rocks found almost everywhere deep beneath the Earth's surface. The HDR system, consisting of the pressurized HDR reservoir, the boreholes drilled from the surface, and the surface injection pumps. These are the pumps, these are the boreholes associated with the plumbing. So this is called the production well, this is the injection well, and this is the stimulated fracture system. This is the heat exchanger, and this is the main power plant. This layer is the hot granite layer from where the heat is produced. The HDR system recovers the Earth's heat from the hot but dry regions via the closed loop circulation of the pressurized fluid. This fluid, injected from the surface under the high pressure, opens pre-existing joints in the basement rock, creating a man-made reservoir which can be as much as a cubic kilometer in size. The fluid injected into the reservoir absorbs the thermal energy from the high temperature rocks surfaces and then serves as the conveyor for the transporting the heat to the surface for the practical use. As the reservoir is formed by the pressure dilatation of the joints, the elastic response of the surrounding rock mass results in a region of the tightly compressed sealed rock at the periphery, making the HDR reservoir totally confined and contained. The hot dry rock system is shown in the figure. Such reservoir is therefore fully engineered in that the physical characteristics like size, depth at which it is created, as well as the operating parameters like injection and production pressures, production temperatures, etc., can be pre-planned and closely controlled. An HDR geothermal energy system is developed first by using the conventional drilling to access a region of deep, hot basement rock. Once it has been determined the selected region contains no open faults or joints, an isolated section of the first borehole is pressurized at a level high enough to open several sets of previously sealed joints in the rock mass. By continuous pumping, a very large region of stimulated rock is created, which consists of an interconnected array of the joint flow paths within the rock mass. The opening of these flow paths causes the movement along the pressure activated joints, generating the seismic signals that is called the micro earthquakes. Analysis of these signals yields information about the location and dimensions of the reservoir being developed. Typically, an HDR reservoir forms in the shape of the ellipsoid with its longest axis orthogonal to the least principal earth. This pressure stimulated region is then accessed by two production wells drilled to intersect the HDR reservoir near the elongated ends of the stimulated region. In the most cases, the initial borehole becomes the injection well for the three-well pressurized water circulating system. One well is for injection well, another well is for the production well, and one is for the heat exchanger. In operation, the fluid is injected at pressures high enough to hold open the interconnected network of the joints against the earth stresses and to effectively circulate the fluid through the HDR reservoir at a high rate. During the routine energy production, the injection pressure is maintained at just below the level that would cause the further pressure stimulation of the surrounding rock mass in order to maximize the energy production while limiting further reservoir growth. The volume of the newly created array of open joints within the HDR reservoir is much less than the 1% of the volume of the pressure stimulated rock mass. As these joints continue to pressure the dilate, the overall flow impedance across the reservoir becomes very slow, leading to a high thermal productivity. The fourth one is the hot dry rock enhanced geothermal systems, that is called the EGS enhanced geothermal system type of resources. In 1980s, the research group of the Los Alamos Scientific Laboratory, USA, pioneered methods of the fracturing the rocks with the pressurized cold water around the end of the injection borehole as shown in the figure. This is the water injection bore. Artificially fractured region is this, where the some heat are lost up. Then the heat outflow, the pump collected this type of heats and then it is used for the district heating. After initial fracturing, the water was pumped down the injection bore to percolate the upwards through the hot rock at the depth of 5 km and the temperature is approximately 250 degrees centigrade before the returning through the shallower return pipes. Using such enhanced geothermal systems, EGS, the complex array of the injection and the return boreholes might in principle enable the gigawatt supplies of the heat to be obtained. However, it has proved difficult to constrain the fracturing so that a large enough fraction of the injected water emerges from the outflow pipes. The injected water leaks into the other fractures and is lost as indicated in figure. Now the last one is the magma geothermal resources. The magma, the naturally occurring molten rock material, is a hot viscous liquid which retains the fluidity till solidification. It may contain gases and particles of solid materials such as crystals or fragments of the solid rocks. However, the mobility of the magma is not much affected until the content of solid material is too large. Typically, the magma crystallizes to form the igneous rocks at the temperatures varying depending upon the composition and pressure from the 600 to the 1400 degrees centigrade. At its site of generation, the magma is lighter than the surrounding material and consequently it rises as long as the density contrast between the magma and surrounding the cooler rocks. Eventually, the magma either solidifies or forms reservoirs at some depth from the Earth's surface, or it erupts. Magma is the ultimate source of all the high temperature geothermal resources. Plate boundaries are the most common sites of the volcanic eruptions. At several volcanic locates, magma is present within the top of the 5 km of the crust. Extraction of the thermal energy from the magma was tested during the 1980s by drilling into the still molten core of a lava lake in Hawaii. However, up to the present, the necessary technology has not been developed to recover the heat energy from the magma efficiently. Economical mining of heat energy from the magma presents several practical difficulties, such as locating such bodies accurately before drilling into them, the prohibitive cost of the drilling, and the longevity of the deployed plant materials in a hot corrosive environment. Now the estimation and nature of the geothermal energy. The dry rock algebra to calculate the potential heat output. We consider a large mass of the dry material extending from near the Earth's surface to deep inside the crust. The rock has density ρr, specific heat capacity Cr, and the cross section is A. This is the area A. This is the depth. This is the Z1. This is the small deviation delta Z, and this is the Z2. At Z1, the T1 is the minimum useful temperature, and at Z2, the T2 is the minimum at the maximum depth. The surface temperature is T0. With the uniform material and the no convection, the G is the rate of the linear increase of temperature T with the depth of Z. If Z increases downward from the surface at Z equal to 0, then T is equal to T0 plus dt by dz into Z. That's equal to the T0 plus Gz. Capital Gz. Capital G is the rate of the linear increase of the temperature. That is dt by dz. If the minimum useful temperature is T1 at the depth of Z1, then T1 is equal to T0 plus GZ1, and Z1 is equal to T1 minus T0 by G. The useful heat content delta E at the temperature of capital T, which is greater than T1, in an element of the thickness delta Z as shown in the figure at the depth Z, is expressed by this equation, that is delta E is equal to rho r A delta Z Cr T minus T1, as well as the rho r A delta Z Cr G into Z minus Z1. The total useful heat content of the rock to the depth Z2 becomes this as per these equations. Finally, we will get E0 is equal to rho r A Cr into G by 2 into Z2 minus Z1 square. Alternatively, let the average available temperature greater than the minimum T1 be the theta, then theta is equal to T2 minus T1 by 2, that's equal to G into Z2 minus Z1 by 2. Then E0 is equal to Cr into theta, that means Ct into Z into Z2 minus Z1 by 2. Assume that the heat is extracted from the rock uniformly in proportion to the temperature excess over the T1 by a flow of water with the volume flow rate capital V, density rho W, specific heat capacity Cw. Then the water is heated from T0 through a temperature difference theta. Assuming a perfect heat exchanger, then the rock of the thermal capacity Cr will cool by an equal temperature range such that V dot rho W Cw theta is equal to minus Ct into d theta by dt. That's equal to the d theta by theta is equal to minus V dot rho W Cw by Cr dt, that's equal to minus dt by tau. The theta is equal to theta 0 exponential of minus t by tau, where the rock cools with a time constant tau is given by Cr by V dot rho W Cw. Substituting the Ct from tau is equal to rho r A Cr Z2 minus Z1 by V dot rho W Cw. The useful heat content will be E is equal to Cr into theta. So the finally E is equal to E0 into e to the power minus t by tau. That's equal to E0 exponential of minus t by tau. And the rate of the heat extraction steadily decreases as the dE by dt is equal to E0 by tau exponential of minus t by tau. Now come to the second estimation, that is the hot aquifers algebra to calculate the potential rate of the extraction. In a hot aquifer, the heat resource lies within a layer of the water deep beneath the ground surface as shown in the figure. We assume that the thickness of the aquifer is H. This is the H. This is the aquifer, hot aquifer. This is the H. This is the surface area. Surface temperature is T0. And this is the material above the aquifer. This is the aquifer where the temperature is T2. The porosity, that is called rho dot, is the fraction of the aquifer containing water. Assuming the remaining space to be rock of the density is rho r. The minimum useful temperature is T1. The characteristics of the resource are calculated similarly to those for the dry rocks, as T2 is equal to T0 plus dt by dz into z, similarly as T0 is equal to G into z. E0 by A is equal to Ca into T2 minus T1, where Ca is the effective thermal capacitance of the aquifer, volume consider. So CA is equal to rho dot rho W CW plus 1 minus rho dot rho R CR into A into H, where A is the area, H is the height of the aquifer. As with the V dot rho W CW theta is equal to minus CR d theta by dt, onwards we calculate the removal of the heat by a water volume flow rate V at the theta above T1. So V dot rho W CW theta is equal to minus CA d theta by dt. So E is equal to E0 exponential of minus T by tau A, and d by dt is equal to minus E0 by tau A into exponential of minus T by tau A. And the tau A is equal to CA by V dot rho W CW. And finally we will get this expression. Now these are the references from where I take the material to produce this lecture. You should go through these references for further knowledge. Thank you.